In this project, a shower drain inside an inclined channel with 120 water input is simulated. A shower drain inside the inclined channel is simulated and analyzed by ANSYS Fluent software. In order to analyze the air and water flow inside the channel, a standard model with the use of a standard valve functions is exploited. A multi-phase VOF model has been used to investigate the two-phase flow of air and water within this channel. The geometry of this project is designed in ANSYS Design Modeler and meshed inside ANSYS Meshing. The mesh type used for this geometry is unstructured. The key assumptions considered in these projects are: simulation is done using pressure-based solver. The present simulation and its results are considered to be steady states and do not change as a function of time. Also, the effect of gravity has been taken into account and is equal to minus 9.81 in y direction. Using a scale mesh section, we can see the dimensions in all three directions. And also we can view the length unit that it is meter in the CFD simulation. From the mesh display section, we can display all the boundaries and surfaces that are related to the inlets, outlets, and walls. There are 120 different water inlets at the top of the channel. Also, there are two outlets, one main outlet and one the side outlet. And also we can see the main wall and the nozzle wall that the inlets are placed on it. The multi-phase VOF model has been used to investigate the two-phase flow of air and water within this channel. The implicit formulation is more stable and the solution convergence is easier. The CFD simulations in which the effect of gravity is considered, the implicit body forces model should be applied. In this case, the effect of pressure gradient terms and volume forces on the momentum equation is significant compared to the viscosity and transport terms. This method is used, the sharp method when the interface between the two phases is completely clear and the phases do not penetrate at all. Also, there are two different phases including air and water. The primary phase is air and the secondary phase is assumed to be the water. And also there is no phase interaction between the phases. So the number of mass transfer mechanisms is equal to 0. In the viscous model, the standard K epsilon model has been used. That is a two-equation turbulence model that allow the determination of both a turbulent length and time scale by solving two separate transport equations. The standard K epsilon model is in ANSYS Fluent falls within this class of models and has become the workhorse of practical engineering flow calculations in the time since it was proposed. Robustness, economy, and reasonable accuracy for a wide range of turbulence flows explain its popularity in industrial flow and heat transfer simulations. Also, it is a semi-empirical model. The standard K epsilon model is a model based on model transport equations for the turbulence kinetic energy K and its dissipation rate epsilon. The model transport equation for K is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning in the derivation of the K epsilon model. The assumption is that the flow is fully turbulent and the effect of molecular viscosity are negligible. The standard K epsilon model is therefore valid only for fully turbulent flows. In the near wall treatment option, we select the standard wall function. Because if the K epsilon turbulence model is used like in this simulation, it is not possible to simulate flow vortex near the walls. So a wall function must be defined, that is a standard wall function for this simulation, to investigate the fluid behavior near the wall. The default materials are air for the fluid and also the aluminum for the solid zone. So we should just add another material for the secondary flow, that it is water. From the operating condition section, we can check and see that the operating pressure is equal to the atmospheric pressure. And also there is one very important point for solving the multiphases, and especially for the VOF multiphase model. In the reference pressure location, we should identify a point at the y direction, in the perpendicular direction in fact, that is very near to the top of the computational domain. In the scale mesh section, we can see that the maximum y magnitude is more than 0.26 meter. So we are sure that in this point y equal to 0.26 meter, there is just air in the domain. So it would be the reference point. And because of that, we identify the 0.26, and also the density of the air is equal to the operating density is equal to the 1.225, that is the air density. Also, as we mentioned before, the gravitational acceleration has been considered in the y direction. Every wall that exists in this computational domain has a sole boundary condition, and all the boundary conditions of all walls are equal to each other. All the walls are a stationary wall with no slip. Also, as we mentioned, there are two outlets, the outlet and the side outlet. Both of them, the boundary condition of both of them is the pressure outlet, and also the gauge pressure is equal to 0. That shows that the flow will exist to the atmospheric pressure. As we said, there are 120 different inputs for the water as the secondary flow, and all the boundary conditions are the same. Velocity magnitude is equal to 2.287 meter per second. And we are sure that just water will pass through these inlets. The simple algorithm in the solution methods section uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. Also, the pressure velocity coupling scheme controls the manner in which pressure and velocity are updated. When the pressure-based solver is used, the scheme can be either segregated, like simple, that pressure and velocity are updated separately, or coupled, that the pressure and velocity are updated simultaneously. ANSYS Fluent provides the following segregated types of algorithms like simple, simple C, piezo, and fractional step or FSM. In general, segregated methods like simple that has been chosen in the CFD simulation are faster per iteration, while the couple algorithm usually requires fewer iterations to converge. For setting under relaxation factors, we should say that the pressure-based solver uses under relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under relaxation factors initially. It is good practice to begin calculation using the default under relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under relaxation factors. Occasionally, you may make changes in the under relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under relaxation factors too much. A cautious approach is to save a data file before making any change to the under relaxation factors and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitude, you should consider halting the calculation and returning to the last good data file saved. You can use the residual monitors dialog box to control the residual information that Fluent software reports. In the equations section, the residual option indicates the name of each variable for which residual information is available. And the monitor indicates whether or not the residuals for each variable are to be monitored. You can toggle monitoring on and off for each variable by turning the corresponding checkbox in the monitor list on or off. The check convergence option indicates whether or not the convergence of each variable is to be monitored. If convergence is being monitored, the solution will stop automatically when each variable meets its specified convergence criterion. You can check convergence only for variables for which you are monitoring residuals. You can toggle convergence checking on and off for each variable by turning the corresponding checkbox in the check convergent list on or off. And finally, the absolute criteria or relative criteria shows the residual value for which the solution of each variable will be considered to be converged. To set this value, manually enter the new value in the corresponding absolute criteria field. And that's it. The standard initialization method has been used, and the water volume fraction is equal to 0 at the initial point. The number of iterations is equal to 10,000. Just click on the calculate button to start the simulation and the solution. We can obtain all the contours, including pressure, velocity, and phase, volume fraction contours on the plane that we will make. To display our desired contour, the first step, we should make a surface. Following this path, we can see the minimum and maximum magnitude in the Z direction, and the best surface to have the two-dimensional contour on that is the Z surface in the middle of the channel. Now we made the plane or the surface, and we are going to show every desired contour on that. Here we can see the volume fraction of the secondary phase, that is water. And also we are able to obtain the velocity contour. Suppose that you are going to obtain for example, the velocity magnitude at the outlet boundaries. Follow this way and obtain the desired report. As it was predictable, the velocity magnitude at the main outlet is more than the side outlet. Finally, this table is a summary of the steps for defining the problem and its solution as a review. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com. Hope you enjoy.